This is part 5 of rivets and bolts. How many of you noticed in part 4 where I made a mistake? I told you we were talking about the ratio of F3 to F4 being y over 1 minus y, all that in parentheses, squared. And multiplying this out, I said y times y is y squared. And then 1 minus y times 1 minus y is going to be 1 times 1 equals 1. 1 times minus y plus another 1 times minus y equals minus 2y. Then I said minus y times y squared is y squared. I should have said minus y times minus y equals positive y squared. At least I wrote it right. Couldn't say it right, but okay, so make a note of that. So let's move on to part 5 here of rivets and bolts. Okay, we're going to look at remember this was our left board. There's another board over here. This is a single shear joint. We just didn't show the board on the right because the stresses in it are a mirror image of the stresses on the left. So all we really need to look at is one side. We're going to look at the bending moments along this nail from the head at the left edge of the board to the middle of the nail where the two boards meet, where it just has a shearing between the two. Okay, as we said earlier in part 4, there's no bending moment at this end of the nail, and there's no bending moment at this end of the nail. But there is a bending moment all along in between here, and it's greatest at 2/3 of the way across, right along in here. Okay, so here's a line I've drawn. It represents the whole 1 inch from the left edge of the board to the right edge of the board. There's our F3. Here's where the line goes up. Here's our pivot point. Where the line goes up, that's all the stress between the wood and the nail that gives us F3. On this side of the pivot point is all the stress between the wood and the nail, which gives us our F4. And we're going to look at, first off, let's look at the bending moment right here at the pivot point. Well, let's look at the bending moment starting here at 0 because you have the incremental unit of area here times that stress equals an incremental amount of force times its distance from there to itself, which is almost 0. So it starts out at 0 at the very end, but it starts picking up, and it's higher here than it is anywhere between here and here. So we can neglect what it is all along there if we're using a bolt that has the same diameter, so forth, the whole diameter through the material and the bolt going through it, because we know it's higher here than it is anywhere to the left of here. So the bending moment here, remember our scales, we pushed our nail that we held with the pliers down against the scales and it withstood 25 inch-pounds of bending moment before it began to bend. Well, the bending moment at this point is going to equal this force, F3, which is 25 pounds, times this distance, which is 2/9 of an inch. We determined that the distance from the left edge to the pivot point was 1/3 of the way across, and this is a 1 inch board. So if that's 1/3 of an inch, and this F3 is 2/3 of the way from there to there, well then it's going to be 1/9 of an inch to there. It's going to be the other 2/9, 3/9 all total, which is 1/3. So it'll be 2/9 from there to there, 2/9 of an inch times 25 pounds, which will give us about 5 or so foot-pounds. Yeah, 5.5555555 forever, or inch-pounds, I mean, of bending moment at this point. So now let's look at the bending moments at all these points between the pivot point and the end. Okay, we've established that the bending moment here at the pivot point is 5.5556 inch-pounds. Let's look at the bending moment at any point between there and there. We'll arbitrarily call a point X. X could be here, it could be here, it could be anywhere between there. And we're going to look at the bending moment at point X. We know that the force of F3 times its distance to X is trying to rotate this nail counterclockwise about point X, but we also have force between the wood and the nail between the pivot point and X pushing up on the nail, which is trying to rotate it clockwise. So our bending moment at any given point X between the pivot point and the right edge will equal the bending moment contribution from F3 minus the bending moment contribution from this force vector. We'll call it FR, with that subscript R meaning right side of this pivot point as opposed to the left side, which gives us F3. X is our distance from the left edge of the board to here. Okay, the pivot point right here is 1/3 of an inch from the left edge. So the distance between X and the pivot point, distance from here to here, is X minus 1/3 of an inch. X minus that 1/3 gives us that, X minus 1/3. Let's call the force vector that represents all the force of the wood onto the nail between the pivot point and point X. We're going to let FR equal that force vector. Like, for instance, if we take a little incremental unit of area here between the nail and the wood, multiply it times the stress, which is 0 here at the pivot point. It's much more here because this line gets further and further away from this horizontal. We'll have our little incremental force vector, and this FR, it represents all these little incremental force vectors between the pivot point and X. And just as F3 is 2/3 of the way from the pivot point to the left edge, FR is 2/3 of the way from the pivot point to X. So the distance between the pivot point and X is X minus 1/3 of an inch, X minus that third. So the distance between the pivot point and FR will be 2/3 of that, X minus 1/3 times 2/3. Okay, the distance between FR and X is the other third, or 1/3 times X minus 0.33333. So 1/3 of all of that, X minus 1/3, is going to be 1/3 X minus 1/3 of 1/3, which is 1/9. The bending moment at X is equal to FR times its distance to X minus F3 times its distance to X. Let's call the bending moment due to F3 M3. Okay, this force F3 times its distance to X, we'll call that M3, M as in Mike, standing for bending moment, and the 3 subscript because it's due to F3. We'll call that M3. And let's call the bending moment due to FR M sub R. Okay, the bending moment at X is MR minus M3. Okay, M3 is equal to F3 times its distance to X, which is 2/9 of an inch, plus this distance, which is X minus 1/3. So 2/9, M3 equals F3 times 2/9 plus X minus 3/9. Well, 2/9 minus 3/9 is negative 1/9. So we can just say F3 times X minus 1/9. Okay, and X is, let's see, F3 is 25 pounds. We determined that earlier. F4 was 100, F3 was 25, F1 was 75. Okay, so 25 times X gives us 25X. 25 times negative 1/9 gives us minus 25/9. Okay, as stated previously, MR equals FR times its distance to X. Okay, here's FR. Here's its distance to X, which is X over 3 minus 1/9. Okay. MR equals FR times X over 3 minus 1/9. we know that FR over F3 is proportional to the bearing surface areas that cause FR and F3. Remember in part 3 we talked about F4 and F3, how F4's bearing surface area was twice that of F3, and the stress along that bearing surface area was also twice as much as the stress along the F3 area, which made F4 4 times as much as F3. Well, we're talking now about our FR, the force that exists between the nail and the wood from the pivot point to X. Now X can be any place along here. If X were all the way to the right, well then FR would be equal to F4. But we're going to look at the bending moments all along here. The bearing surface area that gives us FR is this area between the pivot point and X, which is X minus a third. The bearing surface area that gives us F3 is this first third. So we could say that the force of FR divided by the force of F3, the ratio of FR to F3, it's equal to that bearing surface area of F that contributes to FR divided by the bearing surface area that contributes to F3, all that squared, because the force between these two is going to be equal to their bearing surface area ratio times their stress ratio, and their stress ratio is equal to the bearing surface area ratio, just like F4 stress in our last section was twice as much as F3 stress because its bearing surface area was twice as much. Well, FR, it's a varying amount here, so we can't say it's twice as much, not until we get it all the way to the, not until X goes all the way to the right end of the board. But anyway, this is the formula. It gives us our ratio of FR to F3, X minus a third over a third, all that in parentheses squared. Okay, or we can multiply each side by F3. We can say FR equals all that times F3, which is what we have here. Okay, we can substitute for FR. We set up here MR equals FR times all that stuff. But instead of saying FR, we're just going to write what FR is. Here's what FR is. We're going to take this equation and we're going to write this in place of this. So MR, our MR here, comes down there, gives us MR equals, here's what FR is, all that, X minus a third over a third, all that in parentheses squared times F3, that's what FR is. Okay, and then X over a third minus ninth, we get that from here. That's the rest of our equation here. So, and then multiplying out, we have X minus a third times X minus a third is going to be X squared minus a third X minus another third X minus 2/3 X. And minus a third times minus a third is positive 1/9, so plus a ninth. Okay, and we need to square the bottom too. 1/3 times 1/3 is 1/9. Okay, times F3. Well, F3 is 25 pounds, so we write 25 pounds here instead of writing F3. And all this, we just brought it back down and didn't change it a bit. Ooh, that's about enough of this lesson. We'll get further into it on the next one. We're running out of time.